Okay, so let us next see exercise 4. Here we have to establish these 4 congruences and each one is true for all integers a. So let's start with the first one. Here the modulus is 15, which is not a prime, but it's a product of 3 and 5 which are primes. So we are going to apply Fermat's theorem to those primes. So Fermat's theorem gives us these 2 congruences for 3 and 5. For all integers a. We however want the 21st power of a. So let us first see what that power is congruent to if the modulus is 3. You can write a to the power 21 as this. Now modulo 3, a cube is congruent to a. A cube is the same as a. So this becomes a to the power 7, which itself can also be written as a cube whole square times a. Again a cube can be replaced by a. So that gives us a square times a. Again becomes a cube, which is again finally congruent to a modulo 3. And next let's see for the prime 5. A to the power 21 is expressible in this form. But modulo 5 a to the power 5 is congruent to a. So that means we are getting a to the power 4 times a. So that is again a to the power 5, which is again congruent to a modulo 5. That is, if you write these congruences as divisibility relations, you then get these 2 things. 3 divides a to the power 21 minus a, and so does 5. Now 3 and 5 are relatively prime, so their product also divides a to the power 21 minus a. That is 15 divides this, i.e. a to the power 21 is congruent to a modulo 15. Okay, so this was pretty easy. The others are also similar. Let's see B. In B, because I erased it, let me write the congruence that we have to establish. Here the congruence is a to the power 7 congruent to a modulo 42. So you have to first of all see the primes that give us 42. 42 is 2 times 21, that means 2 times 3 times 7. So we have to apply Fermat's theorem to these primes. A square is congruent to A mod 2, A cube is congruent to A modulo 3, and A to the power 7 is congruent to A modulo 7. Our aim is to show that this congruence is true for each of these primes, and actually we have already got that directly from Fermat's theorem for the prime 7. For the primes 2 and 3, however, we need to do more. So let's first consider 2. 7 can be written like this. Now A square is congruent to A modulo 2. So if the modulus is 2, A square can be replaced by A. Again A square can be replaced by A, and finally we are getting A. And next we consider the prime 3. A cube is congruent to A modulo 3. So you can see that in this case also we are ultimately getting A. Thus 2 divides A to the power 7 minus A. 3 also divides that number, and 7 already divides it, that we saw here itself. Hence, this time we are not even mentioning that 2, 3 and 7 are pairwise relatively prime, because they are. And that is why their product, which is 42, also divides A to the power 7 minus A, i.e. A to the power 7 is congruent to A modulo 42. The other two congruences in parts C and D can be similarly established. In this next one, the modulus is in a factorized form. The modulus is 3 times 7 times 13, and in the last one the modulus is 30, which is 2 times 3 times 5. So I am leaving parts C and D to you, and I am leaving this solution here itself. Let us see the next one. These parts C and D do not have any unusual twist in the solution, so you should be able to get the solutions pretty easily. Even then, if you find any difficulty, you can write in the comment section below. next 5. If GCD of A and 30 is equal to 1, show that 60 divides A to the power 4 plus 59. 59 is 60 minus 1 and 60 already divides 60. So it's enough to show that 60 divides A to the power 4 minus 1. It's enough to show that 60 divides this. Now we are going to first of all use this fact. Since GCD of A and 30 is 1, we have, so what are the prime factors of 30? 2, 3 and 5. So A will be relatively prime to each one of them. Being relatively prime to 2 means what? It means that A is odd. Since A is odd, A plus 1 and A minus 1 are both even. So 4 divides A square plus 1 times A plus 1 times A minus 1, because these two are both even. However, this product you can clearly see is nothing but A to the power 4 minus 1. Okay, so this is one divisibility relation we have got. Also, by Fermat's theorem, since A is also relatively prime to 3 and 5, we are also going to get these things. A square is congruent to 1 mod 3 and A to the power 4 is congruent to 1 mod 5. Do you see the difference between the congruences we are getting here from Fermat's theorem and the ones we got in the previous exercise solution? That's because that is not actually the statement of Fermat's theorem, but the consequence of that, which works for all integers. However, the original congruence we get from Fermat's theorem are these. These are, however, not true for all integers. The integer that you have as your base of the power in the congruence that the Fermat's theorem gives you, it has to be relatively prime to the prime, or in other words, it should not be divisible by the prime. But anyway, we now have these things. So, what can we say about A to the power 4? Obviously, it's also going to be congruent to 1 mod 3 and yeah, this one we already have. Okay, so there is no need to again write it. That is, for the prime 5 we already have what we want, but for 3 we again had to work a little. So we now additionally have these facts as well. So you can now see that 4 divides this and so do 3 and 5. Now 4, 3 and 5 are mutually relatively prime. Note that we are not able to use simply Fermat's theorem for the factor 4 because it's not prime. That is why we had to handle this separately. We however got this again, and the fact that A is odd makes this possible. But for the other factors which are prime, we can apply Fermat's theorem. So their product, the product of 4, 3 and 5, which is 60, also divides this. And that's what we wanted to show. Let us see this next one. Find the units digit of the number 3 to the power 100 by the use of Fermat's theorem. Okay, so that is part A, and part B for any integer A, verify that A to the power 5 and A have the same units digit. To find the units digit of a number, or in other words, the last digit of a number, you have to find the remainder that it leaves when you divide it by 10. That means we have to find 3 to the power 100 modulo 10. Whatever number we are going to get, that will be the last digit or the units digit. And then we also have to prove that for any integer, its last digit, any integer means of course any positive integer, its last digit and the last digit of its 5th power are the same, which is somewhat interesting. Obviously we are going to use Fermat's theorem, but for the primes 2 and 5 because they give us 10 by Fermat's theorem. Note that here A is not, you can actually apply Fermat's theorem in the original congruence here, because here we are not talking about A but first 3, and 3 is relatively prime to both 2 as well as 5. If you want, you can write, since GCD of 3 and 2 is equal to 1 and GCD of 3 and 5 is equal to 1, that is why by Fermat's theorem we have these things. Well, I mean, taking the help of Fermat's theorem to write this congruence, it looks a bit foolish, because it is something that is already known. I mean, you do not need any theorem or anything for this, but still, for the sake of consistency, we have written it like that. And then 3 to the power 4 is congruent to 1 modulo 5. So 3 to the power 100 is congruent to 1 to the power 100, which is congruent to 1 mod 2, and 3 to the power 100, which can also be written as this. This is congruent to 1 to the power 25, that is congruent to 1 mod 5. Again, this time we are not even going to write the divisibility relations. We will straight away write that because of this and the fact that 2 and 5 are relatively prime, we have this. So you can write the last line, which I am not going to write. Hence, the units digit of 3 to the power 100 is 1. If you really multiply 100 copies of 3, whatever number you are going to get, the last digit will be 1. Next, part B. For part B though, because we will be working with any integer a, so we have to apply the other form of Fermat's theorem, or rather the corollary that we get from Fermat's theorem. But we still simply just write by Fermat's theorem, a square is congruent to a modulo 2, and a to the power 5 is congruent to a modulo 5. For all integers a, we write this to indicate that a is general, a is any integer. Alright, so we have what we want for the prime 5, but for the prime 2 we have to work a little more. If the modulus is 2, then what happens to a to the power 5? A square is congruent to a, so this becomes this. Again you can replace a square by a. Again you are getting a square, which is congruent to a mod 2. Thus, a to the power 5 is congruent to a modulo 10. What does this congruence say? It says that whatever remainder these two numbers are going to leave when you divide both of them by 10 will be the same. But we are dividing by 10 means the remainder we will get is the last digit for each one of them, and that is why they will have the same last digit or the same units digit. So you can write the final line, hence the numbers have the same units digit. So let me just end here itself this small video. There are so many other problems, we will solve all of them. And tomorrow, let's because last Tuesday, tomorrow is Tuesday, right? Last Tuesday we did topology, so tomorrow let me go back to differential equations. So that's just it for tonight. See you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.